Okay, so starting from the left-hand side of star, 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 and using conditioning, this is a double conditioning, right? Using a double conditioning and then using the, independence of increments of the original process n, we have obtained thus this far. Okay, so what we have got is that the left-hand side of star, star can be expressed like this. Okay, so now what we do next is we observe that these ij's are IID Bernoulli P. So and this is basically a sum of n minus m many IID Bernoulli P's. So therefore, this has same distribution as this guy. So instead of taking the sum from m minus 1 to n, I could as well take the sum from 1 to n minus n. Both will have the same distribution. They're not the same random variables, but they have the same distribution. Because both are sum of n minus m many IID Bernoulli P's. So therefore, these two have the same distribution. So in particular, these two probabilities are the same for every non-negative integer k. Okay? So therefore, I can replace this guy by this. And then observe that even though the second sum is on n, this particular quantity has nothing to do with n. So I can take that out. I can take that out of this summation, and this comes here. Now what we will show is that this sum here is completely free of n. Okay, we'll do that now. Next. So before doing that, let's just recall that we have been able to express the left-hand side of star, star, star as this. Now note that this is a sum over n running from m to infinity, which is same as running the sum over n minus m running from 0 to infinity. So therefore, we'll replace this n minus m by L. Okay, so we'll run the sum from m to infinity. We'll just put n minus m equal to L. We'll do a change of variable. And then inside, this thing will run from 1 to L. This random variable, this will become 1 to L. Wherever we see n minus m, it becomes L now. And here also this becomes L. Nt minus ns is equal to L. And then the sum is running from L0 to infinity. Now observe that this sum has no m in it at all because we have been able to replace it completely. So these two have become two separate sums. And this guy is just a sum over nm taking all possible values. Because what is the range of ns? Not nm, ns, sorry. What is the range of ns? Ns is a Poisson random variable with parameter alpha times s. Therefore, its range is set of all non-negative integers. So I have taken the sum of ns taking values m, where m runs over the range of ns. So therefore, this probability is just 1. Okay? So this is just 1, and therefore we get this expression. We just get this second sum. So even though it was a double conditioning, by using various properties, we have been able to reduce this to a single sum. So let's see what we have done. As I said, we started with the left-hand side of star, 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 and then express that as a single sum. Okay, now it's time to use the equality of distribution of nt minus ns with n of t minus s, namely to use the stationarity of increments of the process nt. So that will give me that this probability here is equal to same probability except that I replace nt minus ns by n of t minus s. So I'm using the stationarity of the increments. Now what is the advantage of that? So the advantage of that is we can now force a conditioning here. So note that all the ij's are independent of n of t minus s. So we can force a conditioning. So this unconditional probability is same as this conditional probability. That's because n of t minus s is independent of all the ij's. And why are we doing this? It will be clear once we go forward.